Okay, so welcome back to another video. So in today's video we have the following integral. This is integral from 0 to pi of cosine of cotangent x minus tangent x dx. So, we got some trig functions, and inside of a trig function. So I'm pretty sure you can tell by now that this is not going to be like easily integrable to the point that we can integrate it to get like some elementary functions, but there is one method that we're going to do, and I actually did something like this in a similar video last time, and you'll probably know what I'm talking about once I show the work eventually later on. So let's just start. Let me just define capital I as our given function. So it's just 0 pi cosine of cotangent x minus tangent x dx. Okay, now let's actually perform a u substitution, but let me just call this variable t. So t equals cotangent x, and so therefore when I take the derivative of both sides, differentiate, we get that dt is equal to negative secant square x, or negative cosecant squared x dx. But what I can do is that I can actually use our trig laws and then replace the cosecant square with the identity of 1 plus cotangent square of x. So just put the negative outside and we get 1 plus cotangent square x dx. And then further from here I can actually just replace with our cotangent x with just t. So again, dt is equal to negative 1 plus t squared dx, and I'll just divide that by both sides, so we get that dx is equal to negative 1 divided by 1 plus t squared dt. So now we replace with our new integral, and then we have to change our bounds of integration. So when I plug pi for cotangent x, if we're looking at from our interval from 0 to pi, let's just consider this. When I plug pi for x, we're going to get that this is actually just negative infinity. And then if I were to plug 0, well, notice that 0 can actually both approach, it approaches infinity looking from the positive side, and then it approaches negative infinity from the negative. But since we're really integrating this from 0 to pi, so we're just looking at it from the positive direction. So if you take a look at the graph of cotangent x, you plug 0, notice that it actually approaches infinity. So that's what it approaches to. And then we'll just do our replace with our substitution. So let's see, so this will be negative cosine of let's see, we have cotangent x, so that means this will be t, and then minus, so tangent x is also can be rewritten as 1 over cotangent x. So replace that with 1 over t, and then I'll just divide this with 1 plus t squared dt. And now let me clean this up just a little bit, simply because we have to change our bounds of integration, because you have negative infinity as the upper bound and then infinity as the lower bound. Simply, it doesn't work like that because of the larger numbers. So that means we flip our integration bounds. That changes to a negative, but that negative cancels from our negative cosine, so that's nice. So it'll just be positive. And so we have this is cosine of t minus 1 divided by t, and then divided by 1 plus t squared dt. Now, looking at this, now you can clearly see that there's just no way that we can actually continue on using like simple methods of integration, use substitution, integration by parts. It's not going to be that easy from here on out. So what we can do is we can actually go into the world of complex analysis and actually use the following theorem known as the residue theorem. So residue theorem. Okay. All right. So before we use residue theorem, before we actually apply the residue theorem, let's actually go into our world of the complex numbers. Let's consider our complex value function f of z. Z is a complex number. So let's consider to be e to the power I multiplied by z minus 1 over z and then divided by 1 plus z squared. This makes sense for this way. Let me also write for z is a complex number. Okay. It makes sense this way if you think about it, because e to the power I of some input is actually just its polar form. And since we have from our original integral, doing that substitution, we get that there's actually a cosine. So, you know, expanding with the polar coordinates or expanding that polar form, then we actually have that Euler's formula for cosine theta plus I times sine theta for some input theta. So it makes sense to use this function as so. Now you'll notice from the denominator that actually there's actually two simple poles that exist. Simply, let me just write it out in words. Two simple poles exist for z squared plus 1 equals 0. I just wrote it this way. It's simply the same thing, just because the addition, it's commutative under addition. And you'll see that if you were to unfoil this out, you'll get that you have solutions right like this. Z plus I and then z minus I. That's simply just expanding this out equals 0. And you'll see that z1 and 2 is equal to both positive and negative I. Now let's actually consider the following contour of the complex plane. I'll just call that gamma capital R. So give me 1 second to construct this little contour we're gonna analyze. Okay, now so as you see from this construction of our contour here, also define this this whole contour as, well, the whole plane as gamma R, and then I also define this little semicircle over here as just lowercase gamma capital R. Okay. So you'll notice that we have our two solutions of the two simple poles, plus and negative I, but you'll notice that negative I lies outside of the contour, so you have to calculate its residue, but positive I lies inside that contour. So meaning, using residue theorem, we can actually apply this theorem to help calculate our this integral. So we're gonna so basically defining this contour integral. So we have the contour integral of capital gamma R, and then f of z dz is equal to, so this is basically just 2 pi I, and then multiply with our sums. Let's see, j equals 1, and then the residue of f of z and then zj, where f of z is our complex value, then z sub j is like how many poles do we have to calculate to calculate from that contour. Okay, so now we use this. I'll also write out the formula for finding the residue. So finding the residue of f of z with the pole z sub j is just equal to the limit as z approaches z sub j of z minus z sub j, and then multiply by f of z. Okay, good. Now I'll also state that, here, let me move this, and I'll put this right over here, so at least I have some space to work with. Now we notice that since z equals I is the only pole in capital gamma of R, z is equal to I is the only pole, let me write, of f of z that lies inside the contour capital gamma capital R, then really calculating this residue is not so bad over here. So f of z is equal to, or the residue of f of z at the pole I is equal to the limit as z approaches I of z minus I, multiply our f of z, which is just e to the power I z minus 1 divided by z, and then divided by, and I'll expand this out, this is z minus I multiplied by z plus I. We further continue from here. This means this is limit z approaches I of e I z minus 1 over z, then divided by, let's see, z minus I cancel, so we're just left with z plus I. We just plug in I, so that means e I, and then I minus 1 divided by I, then divided by I plus I. let's actually simplify the numerator first. Okay, so let's just simplify. Let's actually take a look at simplifying just the inputs of our polar form. Okay, so let's calculate this our input over here. So let's start with so we have I minus 1 divided by I. Let's actually rewrite this a bit so we get that this is the same thing as I divided by 1 minus 1 divided by I. Just use the butterfly method so we get that this is I squared minus 1 divided by I. Now I can actually simplify this out a little further. I squared is just negative 1, so we get negative 1 minus 1 divided by I, which is simply just equal to negative 2 divided by I. And multiplication of complex numbers, or division as well, you don't want I to be in the denominator, so you just multiply and divide I. So that means this is just negative 2I, and then divided by I squared, which put it simply, this is just, let's say this is negative 1, so that means this will just be 2I. And now continuing further, so we have that I, and then replace I minus 1 over I. That's just 2I, just distribute that. We get that this is 2I squared, therefore it's just equal to negative 2. Okay, so now we go back to here. So far we have that residue of f of z evaluated at the pole I is just equal to e to the negative 2, and then I plus I is just 2I. And we'll just leave that the way it is for now. And also underline this in black just to reestablish what we have. So now next thing is, so let me go back to the original formula. So gamma r f of z. So notice that when we're evaluating contour integrals, we're evaluating this whole integral. So this is including the semicircle and the real line itself from negative r to r. So if we expand this, that means, or rather not expand this, but rather rewrite this in a way. So this is our contour of the semicircle of capital R. So that's f of z dz. And then add that with our integral from the real line. And because we're dealing with, this is just the real part. This is because this is the x-axis, so this is the real axis. So I'll write this in terms of limits. So this is the limit as capital R approaches infinity from r to negative r of f of x dx. Now for evaluating this little our semicircle arc, so let's consider a parameterization. So let's see. Let me not write it like that. That integral symbol like that. It's just supposed to be. So semicircle f of z dz. Consider parameterization. So we'll call this z theta, which is equal to our radius capital R of our polar form e to the power I theta, such that theta is in between, so you see it starts from 0 and then go to pi, and that's just from the closed interval. But you can clearly see that if we apply Jordan's lemma, so apply Jordan's lemma, then you'll see that, I'll write the results for using this theorem. You will see that the limit as r approaches infinity of our semicircle, which is lowercase gamma of f of z dz, is actually just going to equal 0. So this means this the line integral from of the semicircle arc slash path is actually just going to equal 0. So now last thing we have to do is just calculate our so really we're just left with the limit as r approaches infinity from negative r to r of f of x dx. But since we said that that's also equal to this whole contour integral, the capital gamma of r, but we also use the little residue theorem, so we can just equate the two together. So this means this is just from this formula here, we said that that's 0, so we're just left to calculate this, and we set that equal to the residue theorem formula from over here. So this is just 2 pi I, and then multiply with the only pole we evaluated was e to the negative 2 divided by 2I. And then you'll see that the 2 i's cancel, so we're just left with pi and then e to negative 2. Okay, we're pretty much done, but well, I shouldn't say but like another way if you want to explicitly see this for yourself is that if I were to write this whole contour integral again, so f of z dz. Now if I actually just expand, where is it? So if I actually just expand our f of z function out, this is, let's see. So this is, we're dealing with the from r to negative r, which is the infinity, so I'll just put it back. Okay, so this is, so using the polar form, this is equates to cosine of, so in this, I'll put this in the parameters of x, so 1 over x divided by 1 plus x squared dx, okay, and then plus I, that's like our imaginary part there, and then this time this will be sine of x minus 1 over x divided by 1 plus x squared dx. Okay, but you can clearly see that now we set these two equal to each. Now we set these two equations equal to each other. We can see that this is actually our given, and then over here it's just equal to 0 because simply from this side there are no imaginary parts. So this means the final answer we can actually come to the conclusion to is that so let's see. So I'll just rewrite the capital I from what was given. That's the new I from here. So that means cosine of x minus 1 over x, then divided by 1 plus x squared dx is equal to, what is it? Pi divided by e to the 2, simply just because negative 2, negative reciprocal, just move that down. And this is simply because we just equate parts to each other, parts. So really, this is undoing that substitution from here and going back to the original integral, so therefore we can come to the conclusion that, let me just write this back, our final answer for our given integral, the integral from 0 to pi of cosine of cotangent x minus tangent x dx is equal to pi divided by e squared. And there you have it, like so. All right, that's pretty cool if you ask me.